Okay, I'm going to try to do a little 5-minute short video on my iPhone describing SN2 reaction. If this works and it's helpful, I might try doing this more often for little reactions so you can go up on Moodle and refresh your memory about them. Okay, the SN2 reaction. Now, SN2 reaction is a substitution reaction. That's what the S stands for. The N stands for nucleophilic, which means that there's a nucleophile involved in this substitution. And the 2 means that really there's a concentration of 2 things that are important for the velocity or the speed of this reaction. Okay, so first I've got this model here. This is kind of cool. This was sitting in the organic lab, and it's a little different molecular model than what you've seen before. Now if you look at it, and I can twist it enough, you'll see this is just our typical tetrahedral shape, right? Now, these SN2 reactions, and a lot of the substitution reactions and elimination reactions we're going to be talking about soon, all involve alkyl halides as the substrate. You'll hear that word more often in lecture, the substrate. Really, the substrate is the molecule at which the reaction is occurring. So here, if you can imagine, this is an alkyl halide. It's got this central carbon, this big sucker right here. It's got a halogen attached to it, the yellow ball over here, and then 3 other substituents. Okay, and these can be lots of different things. Okay. Now we said what makes alkyl halides reactive and interesting is really they're just alkanes with this bond. Okay, this carbon halogen bond, and this is what makes the alkyl halide reactive. This is a polar covalent bond, really with this electrophilic halogen taking the lion's share of these electrons, and this is what allows substitutions to occur pretty readily. You can imagine this halogen leaving with the electrons, okay, and something else coming in and substituting for it. Now we've got 2 main mechanisms through which this substitution occurs, and the SN2 we can think of as really involving the nucleophile, in this case is in red, pushing out this halogen as a leaving group. Okay, now how does it push it out? Okay, the SN2 we sometimes think of as having a backside attack. So we have our alkyl halide here. We're going to try to substitute this nucleophile, and this could be anything. Really, it could be another halogen. We talked about nucleophiles in the first semester. Anything with a lone pair, negative charge, can be a good nucleophile and be attracted to the positive charge or partial positive charge that's present on this big carbon right here. Okay. In an SN2 reaction, the way the substitution occurs is through a backside attack. The nucleophile comes in to the opposite side of the carbon from which the nucleophile is and replaces it. Okay. The halogen left as a leaving group and landed on my keyboard. Okay, replacing it was this new nucleophile here. Okay, now what's cool about this model, you may or may not have noticed, let's do it again, is looking at the position of these 3 other substituents on the carbon. Okay, I'm going to take this out just for a second, put it back the way it was. Here we've got our alkyl halide with our cool tetrahedral geometry, and what we see is really an inversion of this tetrahedral geometry as this nucleophile comes in and substitutes for the leaving group. Boom. Okay. Now this has consequences on the molecule. We have another different molecule, a substituted molecule here, and you might imagine because we've changed or inverted this tetrahedral geometry, we've also inverted the stereochemistry of this. Okay. Now, you might be thinking, well, what's left? We've got this leaving group that's left. It took these electrons with it, so it's negatively charged. It could be chloride, bromide. It's now a nucleophile. It could come back in and do the opposite reaction, boop, bringing us back where we started before. And that's true. Okay, so we can think of the SN2 reaction as really being a competition. Each of these nucleophiles has the potential to attack from the backside and kick out the other one. So how is this productive at all? All we're doing is going back and forth, back and forth. Well, obviously for a reaction to proceed, we're going to have to think about which of these is the best nucleophile? Which one has the characteristics that will make it win this competition and therefore generate one type of product over another? Okay, we'll talk about the characteristics of nucleophiles, what makes them good, what makes them bad. We'll talk about the characteristics of the substrate, what makes them a good substrate for SN2, what makes them a bad substrate for SN2. We'll talk about leaving groups, what makes something a good and a bad leaving group, and we'll talk about some other conditions which promote this type of substitution reaction from occurring.